We're given a circuit that has a capacitor. At t equals 0, the switch moves from position A to position B. So before t equals 0, the 6-volt source here charges up the capacitor. At t equals 0, the switch moves to position B and the capacitor starts to discharge through these two resistors. Now we have a variety of things we want to do with this problem. The first thing is just to write the differential equation governing the capacitor voltage, V of t, for t greater than 0. So to write the differential equation governing the voltage for t greater than 0, we need the circuit for t greater than 0. So my 6-volt source is no longer connected to anything, and my capacitor, which has a capacitance of 1 microfarad, is connected to this 2 kilo ohm resistor in series with this 3 kilo ohm resistor. So really, since the voltage source isn't connected to the capacitor, we don't really need to worry about that. That's not even part of this problem. So my capacitor voltage is V of t, so let me label my capacitor current I of t. So I of t here is C, so 1 microfarad times dV by dt. Positive this direction. Remember that I have to stick with the passive sign convention to make this work. Now I don't have to remember anything about the capacitor voltage current relationships. All I have to apply now is KVL, KCL, and Ohm's law. So if I do KVL around this loop, I have a minus V of t for the capacitor voltage. If current is going in this direction, then my passive sign convention says that that's positive and that's negative, that's positive and that's negative, so it's a minus 2 kilo ohms times 1 microfarad dV dt. So the current through the 2 kilo ohm resistor minus terminal first on the 3 kilo ohm resistor, so 3 kilo ohms times the capacitance, 1 microfarad, times the derivative of the capacitor voltage with respect to time. That brings us back to our starting point, so that all sums to 0. Let me change the sign on everything. So I have a V of t, and I have a 2 times 10 to the minus third plus a 3 times 10 to the minus third, which gives me 5 times 10 to the minus third dV by dt is equal to 0. There's my differential equation governing the capacitor voltage. Now in part B here, I want to find the time constant of the circuit from the differential equation. The standard form of my first order differential equation is going to be dy by dt plus 1 over tau times y is equal to 0. So what I do is have a multiplicative factor of 1 on dy dt, and then my time constant is the inverse of whatever the coefficient is that multiplies y. If I take this equation and put it in that form, I divide through by 5 times 10 to the minus third. So I have dv by dt plus 1 over 5 times 10 to the minus third. V is equal to 0. So tau is equal to 5 times 10 to the minus third seconds. Now let's go to a new slide to finish up the problem. Part C. Find the tau from the capacitance and the equivalent resistance seen by the capacitor. So for an RC circuit, for a first order circuit with only one energy storage element, where the energy storage element is a capacitor, the time constant, tau, is just the equivalent resistance seen by the capacitor times the capacitance. Now tau is a property of the circuit for t greater than 0. So remember that the circuit for t greater than 0 was this one, and we want the equivalent resistance seen by the capacitor. This is essentially like a Thevenin circuit problem. So we're going to take the capacitor out, look at the terminals across which the capacitor is connected, and calculate an equivalent resistance. If I do KCL here, these two elements are in series, so Req is just the sum of the two individual resistances. So Req is 5 kilo ohms. So tau from this equation is Req times C, so that's 5,000 times 1 times 10 to the minus 6th, which is 5 times 10 to the minus third seconds, which is the same answer we got from the differential equation, as it should be, because there is only one time constant for the circuit. In part D, we want to find an initial condition on the capacitor voltage. So the voltage at t equals 0 plus just after this switch moves to position B. Well, in order to find initial conditions, what we usually rely on is that the capacitor voltage can't change instantaneously. So let's look at the circuit for t less than 0, and in fact for t equals 0 minus, and we'll assume that this switch has been in this position for a long time. So I have a 6-volt source, I have a 1 microfarad capacitor, and this is my voltage, V at t equals 0 minus. But if this switch has been in this position for a long time, the capacitor has had a chance for everything to become constant, since the input voltage is a constant. If everything's constant, then the capacitor looks like an open circuit. If this is an open circuit, then this voltage is just 6 volts, so that's the initial voltage across the capacitor. Again, the capacitor voltage can't change instantly, so the voltage at t equals 0 plus, which is what we want, is found by determining the voltage at t equals 0 minus. So finally, we want to find the voltage across the capacitor as a function of time for t greater than 0. That voltage after this switch has isolated the capacitor from the voltage source. Now, this is a first order circuit, and the source, there is no source connected to the energy storage element during the time of interest. For t greater than 0, this source is not connected to the rest of the circuit. It doesn't affect v of t anymore. It's only used to determine an initial condition. So for this case, the form of the solution, so since this is a natural response of an RC circuit, or really the natural response of any first order circuit, the voltage, V of t, is going to be the initial condition, V0 e to the minus t over tau. V0 is 6 volts, so V of t is 6 times e to the minus t over 5 times 10 to the minus 3 volts for t greater than 0. So there's my answer for part E.